Hello students, now we are going to start the next chapter, that is Eigen Values and Cayley-Hamilton theorem. First, now write the definition of eigenvalue, which are also called characteristic root, latent root, proper values. They have many names. So what is its definition? Let A be a square matrix of order n, right, and a scalar lambda is called its eigenvalue if and only if there exists a non-zero column matrix X which has the element, let x1, x2, xn, because the order of A is n, so n-rowed column vector, such that A into x is lambda into x. So such value of lambda which satisfy this condition is called eigenvalue. For practical questions, for working method, what we say, we will just put A minus lambda I determinant equal to 0, and from this we can get the value of lambda, which will be the eigenvalue. So to find the eigenvalue, what we have to do, you will be given some matrix, A, which will be a square matrix of order 2, of order 3, or sometime it can be of order 4. So you write that matrix, and you have to write the matrix which is I identity matrix of same order, right? Then you put these things in this equation. This is A minus lambda I determinant. So this determinant will be, this will be A minus, here it will be lambda and then I. Then you subtract these two matrices and you'll get one matrix of which you have to take the determinant. Determinant, you can apply properties of determinant to solve it, or you can directly expand this. So by expanding, you will get some relation which you will put equal to 0, and we will solve the value of lambda from that relation. Let us now see this question. Determine the eigenvalues of this matrix A, which is square matrix of order 3. So for this, what we will write, consider A minus lambda I determinant equal to 0. So we'll start the question from here whenever we have to find the eigenvalues. So A is 3, 1, 1, 2, 4, 2, 1, 1, 3. Lambda we need to find identity matrix of same order, that is of order 3 is this, and then you put the sign of determinant and equal to 0. So you will take the difference of these two matrices. When lambda multiplied inside, it will be lambda 0, 0, 0, lambda 0, 0, 0, lambda. A matrix will remain same here. Now we will subtract these two. Don't forget to put the sign of determinant here. So if we subtract these, it will be 3 minus lambda. 1 minus 0 is 1. 1 minus 0 is 1. Corresponding difference we have to take. Then it is 2 minus 0. 4 minus lambda. 2. 1, 1, 3 minus lambda. Determinant equal to 0. So you now can see that only the diagonal elements have changed here. All the remaining elements are same. So we have to subtract lambda from the diagonal elements. Rest of the matrix A will remain same. So you can directly write from here only that this is matrix A. For the questions you will do, when you write A minus lambda determinant, you can directly write it will be determinant of 3 minus lambda, 1, 1, right? Then 2, 4 minus lambda, 2, 1, 1, 3 minus lambda. So you can directly write this thing, and you have to put equal to 0, the determinant, this one. So now how to solve this determinant? Now we have this method called expansion method. You can expand this with respect to first row or any row, or you can apply some properties so that you have the matrix which is quite easy to solve. So here I am going to apply the property method. Now this is 1 1, so this is easy to make 0 here by subtracting, or you can make 0 here by multiplying third row by 2 and subtracting from second row, whatever method you prefer. So I am doing it here, column 1 minus column 2 minus column 3 on column 2, right? So I am just applying this because all other elements or rows are containing lambda, so that is not easy to make 0. This is very easy for me, 1 minus 1. So column 2 minus column 3. 1 minus 1 is 0. Then 4 minus lambda minus 2. It will be 4 minus 2 is 2 minus lambda. It will be 2 minus lambda. Here 1 minus 3 plus lambda. So it will be minus 2 plus lambda. 1, 2, 3 minus lambda as it is, because we have operated only one operation. Now this is 3 minus lambda, 2, 1, and you can see in this column 2 minus lambda or lambda minus 2 is common. So I have written it lambda minus 2 common from the second column. So 0, lambda minus 2, it is minus lambda plus 2, so minus 1 will remain. Lambda minus 2 is common, so it is 1 here. The rest of the terms are as it is. Right? Now this is 1 minus 1 and 1. Again you can add these two to get one more 0. So which will be equal to what? Lambda minus 2 is already common. 3 minus lambda 0 1 as it is. Here I am going to add row 2 and row 3 at the place of row 2. So I am adding row 3 to row 2. So it will be 3, it will be 0, it will be 5 minus lambda, 1, 1, 3 minus lambda as it is. Now we have two zeros in one column. You can make two zeros in two rows or two columns. So now we have this thing. So we can expand with respect to the second column. So by expanding this means we have to write the sign of the cofactor plus minus plus minus. So minus lambda minus 2 is already common. Then expanding with respect to this element means cross multiplying. So this is minus lambda minus 2, and cross multiplying these will be 3 minus lambda into 5 minus lambda minus 3 equal to 0, because we have to solve the lambda value which make this thing 0. So all these are 0, equal to 0. So from here you have lambda minus 2 into this thing, this multiplying these, 15 minus 8 lambda plus lambda square minus 3 is equal to 0. So this is minus 2 lambda minus 2 lambda square minus 8 lambda plus 12 is equal to 0. Now we have to factorize this. This is the factor which is already outside. Now factorizing this will be 6 and 2 the factors. So this will be so the factors of this are lambda minus 6, lambda minus 2. You can factorize this 12. 12 is 6 into 2 and 6 plus 2 is 8, both negative, equal to 0. So what are the values of lambda from here? Equating each of this is equal to 0, you will get lambda is equal to 2, lambda is equal to 6, lambda is equal to 2. So these are the Eigen values of A. Right? This is the method of solving the eigenvalues.